For this video I wanted to have a look at the Edexcel Gcse 9:1 formulae, and these are the ones that you need to know. Now I think it's a very good sheet to look at, and you can see the foundation ones here are in dark grey, so I'll put foundation by these ones here just so you can see them more clearly. Notice that the trigonometric ratios are new to foundation, okay? And just finishing these ones off so you can see. And then we've got the higher tier formulae. So it doesn't mean you have to if you're doing a high, you don't have to know the foundation. It's assumed that you will know those as part of your higher paper, but the extra ones that will just appear on the higher and not the foundation, I'll label in H, with a H for you, so you can have a look at those. There we go. So let's start with the higher ones first, and we'll go through those, and then we'll look at some of the foundation ones. And like I said, if you're a higher student and you've looked at the higher ones, if you know all the foundation ones, then that's you done. If you're a foundation student, you can skip forward if you don't want to know the higher ones, and then you can just see when the foundation ones appear, and I'll go through those. So which one shall we start with? Well, the first one I'm going to look at is the area of a triangle formula. Now, if you were looking at the foundation paper, then if you saw a triangle like so, which was right angled, and we call this C, A and B, very similar to how this one's labelled here, then the area of this triangle, as you would all know, is the area of the triangle would be half times the base, which is A, times the perpendicular height, i.e. the height at right angles to the base. And you could write that as AB over 2, and that would be in units squared. But in this diagram here for the higher paper, what we've got to think about is that this angle may not necessarily be a right angle, okay? So if this wasn't a right angle, then the area of the triangle would be really similar to what we had if it was a right angle. So we'd have a half times A times B, but all we're doing is timesing by this correcting factor, which is called the sine of C in this case. Now, for those higher students who know trigonometry reasonably well, you should know that the sine of an angle lies between 1 and minus 1. So this isn't a very big number at all. But as this angle here changes, so does sine of C, and that has an effect on the overall area. So if we took a triangle like this, which definitely doesn't look right angled this time, and I labelled it the same, and let's just label these sides here, and let's just use this angle. We could use any angle we like. Then we can say to ourselves, well, the area of the triangle, if this was a right angle, would be a half times the base times the perpendicular height, which would be B. But we know that this one isn't a right angle, so all we have to do is times by the sine of the angle that makes A and B happen. Okay, so if you think about it, if you have A and B, they make this angle, and that's the angle that we have to have here, so it would be the sine of C. Now, if I wanted to, say, look at this angle here and use this one, then what would the area of the triangle be? Well, the area of the triangle in this case would be a half times, well, let's orientate the shape round a little bit here. And I can just write it out again, it doesn't matter. So what we'd have is the area would be, let's choose, this is the base, C, times, let's pretend this is a right angle, so C times B, but we know it's not a right angle in this case, necessarily, so we times it by the sine of the angle which the two sides we've chosen make. Okay, so there's the angle, it's sandwiched between C and B, so that's the angle we choose. Now if we go back to the actual formula sheet, then we can do a real quick shortcut and we can say, right, okay, if we want to use this angle here, then the area would be a half times B times C times, well, what's the angle? The angle would be A, so times sine of A. But however, if we wanted to use this angle instead, C, the area would be a half times, well, how is that angle made? Well, we're using A and B, so it would be a half times A times B times the sine of the angle, well, that would be C in this case. Or, if we wanted to use this angle here, the one that A and C make, then we'd have the area would be a half times A times C times the sine of B. Now some of you may wonder, why do I have to write B here and I could write C there instead? Well, you can change these around, but generally the formula sheet will have these in alphabetical order. So there's no mathematical law which says you can't have C times B instead of B times C. Okay, so the reason I've done this one first is because the nice thing about this is that all of those areas are the same. So we can then look at doing the sine rule leading on from the area of the triangle. Now, how can that work? Well, if we know all those areas are the same, then we can just put two of those areas, we can just choose two of them, let's just choose these two, and let's put them equal to each other. So we can say a half times B times C times the sine of A is the same as this one, a half times A times B times the sine of C. Well, if we double both sides, we would be left with BC sine A equals AB sine C. And if we divide both sides, say, by BC, what would happen? Well, this would cancel here, and this would cancel here, so we'd be left with sine A. And in this case, we'd be left with A sine C over C. And then if I divided both sides by A, well, look what happens. We're left with sine A over A is sine C over C. Now, that's exactly the same as writing A over sine A equals C over sine C. So what you can do is, you can try and put these two equal to each other, and you will get A over sine, you'll get B over sine B is C over sine C. Why? Because you've only used these two angles here. And then if you wanted finally to put these two equal to each other, then you would be left with A over sine A is B over sine B. So hopefully that kind of explains to you why if all of those three things are equal to each other, then that's how the sine rule follows on. Okay, that's why all of these three are equal, because you can show that these two are equal, these two are equal, therefore these two must be equal. Okay, so that's the sine rule explained, and don't forget, if you're finding an angle, then you can just write this one like this. Sine A over A is sine B over B is sine C over C. Okay, so don't be worried too much about that. So let's move on to, I think, the cosine rule now. So let's have a look at that one. Well, the cosine rule, I think, is quite a nice rule to remember. It's not too hard as people make out. So the nice thing is, let's just copy this diagram here and let's make ourselves a bit of room. So let's move this over here. So let's create a triangle that looks like the one on the formula sheet. And label this A, B, and and C, and then C, little a, and little b here. Now, on the formula sheet, the only thing I want to have a little peek at is we're using this angle here, A, in this instance. And I'll show you how to use the other two as well, just a quick way of remembering. Well, what you can do is, you can say, right, okay, I want to use this angle A here. So my advice is, pretend again that it's a right angle triangle. So what you would get is B squared plus C squared would be equal to A squared. That's if it's a right angle triangle. So all you kind of have to think about it is, well, it's not a right angle triangle, is it? And that's why 2BC cos A comes in as a correcting factor. And I put a little hat on here to show that it's an angle. So the only thing you really have to remember about the formula is what to take away from the left-hand side. Now, say for example, you want to involve this angle instead, angle C. Well, my advice is pretend that it's a right angle, and what would you have? Well, you'd have A squared plus B squared would be equal to C squared in this case. Now we know it's not necessarily a right angle, and when you're using the cosine rule, it won't be a right angle. So what do we have to take away? Well, always it's going to be 2 times this number cos the angle that we've chosen. So we'd end up with A squared plus B squared minus 2AB cos C is C squared. And I think a lot of you probably know now how to use angle B straight away. Well, let's try it. Let's pretend it's a right angle. So we'd end up with A squared plus C squared would be equal to B squared. And the only thing you've got to remember is to take 2AC cos B away. Now, for those that are okay with that, I hope that you're okay with rearranging it if you had to find the angle. So I'll just choose, say, this one, and we'll look at that one. So if we have A squared plus B squared minus 2AB cos C equals C squared, and I wanted to find the angle, well, all you have to do is just rearrange using the formula that we already have. So what we can do is, we can times both sides by -1, so we'll change this sign here, this becomes a plus, and this becomes a minus. We can leave all of this on this side here, so we'd have 2AB cos C, and then all we have to do is add A squared and add B squared. So we just have A squared plus B squared, the minus C squared is there for us, and yep, you've got it, we just have to divide both sides by 2AB, and there we have it, we have cos C. And so if you want to find C, you just have to do inverse cos or arc cos of both sides, and that will be your angle. So what I suggest you do is try and rearrange this one yourself and this one yourself for cos C and cos B respectively. So that's the cosine rule, and some quick tips on how to recall that in the exam under pressure. Just think of Pythagoras and it will get you out of trouble a lot of the time. Now the next one I will look at, and I'm not going to prove this from first principles, this is just like giving a couple of tips that I've learnt over the years. Let's look at the quadratic equation. So let's get rid of some of this stuff here, get it out of the way. Now for this one, I would personally write this in a slightly different way, because if we have ax squared plus bx plus c equals 0, then if we wanted to look at this as a function, say y equals ax squared plus bx plus c, then this quadratic would have a line of symmetry, and for those that know what the line of symmetry is, well, it's x equals minus b over 2a. Now, that's why I wanted to mention this, because when you look at the formula given here, try and think to yourself, it's got to have the line of symmetry in it somewhere. So if you write out what it says on the actual sheet here, which you won't have. So if I say formula sheet, please don't think that's what you're going to get. These are things you're going to have to remember. It gives it like this. Whereas if you write it like this, minus b over 2a plus or minus the square root of b squared minus 4ac over 2a, at least then you can see the line of symmetry. So that helps you. So if you didn't know that was the line of symmetry, well, you do now, because what that means is if you have a graph like so, and you're wanting to know the point where the minimum happens, or you're asked to find the line of symmetry, you can now just use part of this formula here to find it straight away. And if you're ever asked to find the discriminant, or to work out whether it has real, repeated or no roots, then this part here is called the discriminant, b squared minus 4ac. So try and think about saying the formula a lot of times. Now to say it, it's probably easier to say it in this form, so I'll just say it as I go over it. Minus b plus or minus the square root of b squared minus 4ac all over 2a. So I'll say it again. Minus b plus or minus the square root of b squared minus 4ac all over 2a. But then when you write it out, just try and split it up in this way, and then you'll see, oh okay, this is the line of symmetry and this is the discriminant. Okay, so that's the quadratic equation, and there's some plenty of videos out there on songs and things you can sing to help you remember it, and believe it or not, I'm not going to be doing that right now. So let's have a look at another one. In fact, the last one that higher students are expected to know, as opposed to the foundation ones, which you're supposed to know as well. So for the higher ones, let's have a look at what a cuboid would look like. So that would be the cuboid, and if I just draw that out, so it's best to do two rectangles and then just join up the points. Apparently Archimedes worked this out, and that is that if you take a base like so, and then a point on the very top, which reaches the very top, join all these points up, you'll make a nice solid, and the volume of that solid will always be a third of what the whole container would have been. So if this was A, this was B, and this was C, the volume of the cuboid, as you know, is just ABC, or A times B times C, but the volume here of the actual pyramid in blue would be ABC divided by 3. So basically, if I melted down 3 of those pyramids and poured them into the entire cuboid, it would fill it up completely. Okay, so that's quite an interesting one. One that's not on the formula sheet to have to remember, so don't quote me on this, but I can't see it on here, I'm just going to double check, is the cone. Okay, so I'm pretty much assuming that they'll tell you what the volume of the cone is in a question. But if we just draw a cylinder, so two circles, and let's just join these up. Then again, Archimedes noticed that if we choose a base here, and any point on the very top, now it doesn't really matter where this point is in red here, it could be here or anywhere, just like this blue one here could have been here or there or at a corner even. Okay, so for example in this one that I did first, I could have joined all of these points up, okay, and I still would have melted 3 of those to fill the whole cuboid. In this case, if I choose the base, I'll do that in blue I think, if I choose the base and then a point on the top and join them up, I will make a cone. So I think you know what the volume of a cone should be then. The volume of a cone should be the volume of the cylinder, which is the area of one of the bases, pi r squared, times by the height, which is given here, the perpendicular height, but then the volume of that cone must be a third of the cylinder, because again, just like we had in the first case, 3 of those melted down cones would fit exactly into the cylinder. That's an Archimedes principle. So that relationship of the factor of a third is really important in both of these cases. So if you know the foundation one for the area of a cylinder, then you definitely know the volume of a cone without doing too much. And if you know the volume of a cuboid on the foundation, you now know the volume of a pyramid. It's that ratio of a third, so that fraction is what you times by to convert from one to the other. Okay, so think of those two and that should help you. So really they're the higher ones done. So if you're a higher student and you know all the other foundation ones, then that's fine. Then this video is finished for you. But if you're a foundation student, we're just going to pick through some of the foundation formulae now. Well, the first foundation one to look at would be the area of a rectangle. If you know that area is measured in units squared, i.e. the area that this little square would be, say it's 1 centimetre by 1 centimetre, the area would be 1 centimetre by 1 centimetre, and 1 times 1 is 1, and centimetres times centimetres give you centimetre squares, so that would give you 1 centimetre squares, or 1 square centimetre. Now, in this case, if you just kind of imagine that you're filling this up with those little square centimetres, let's just say you tried that, then you'd be doing something to do with the heights here, or the lengths of these ones going across here. So if you look at each of these little centimetre squares, you're always looking at timesing these numbers here, or the sum of these numbers, so we'll call this L, because it's the same as this one, times the height of these ones, and the height of these ones go to make up W. Okay, so we're always doing a length of sorts times a width. Now in the case of a square, the length and the width are the same. So if you wanted the area of a square which measured, and let's just make one, L by L, then the area would be just L times L, which is L squared. But in terms of a rectangle, all we need to do is just think, okay, there's my rectangle. Imagine it's a square if it helps, and just think, well, I've got to times this side here by this side here. So length times width, because that's exactly what you do in the case of a square to get the actual area. You do a length times a width. And just because they're the same, it doesn't matter. The principle is exactly the same. You then get a coverage of an area. You actually create an area. Okay? So rectangles aren't too bad. From the rectangle one, I would like to look at the simple case of a triangle. So if I take this rectangle here that I've already done, if I just reproduce it here, and I'll label this side A and this side B. Well, it's a rectangle, so all the vertices are right angles, and the area, well, the area is just A times B, which is the same as AB. But if I wanted to create a right angle triangle, then if I wanted the area of one of these, I would just have to halve it, wouldn't I? Because you can see here that I'm cutting the rectangle exactly in half. So if I wanted the area of the triangle, and if I label that A, B, C in this case, as long as it's a right angle, I'm just going to have A times B, which is the whole rectangle, but then halve it. Okay? So one way of thinking about it is base times height, and the height's really important. It's got to be one that's at right angles, all divided by 2. So base times height all over 2. But if we look at the actual formula sheet, what we have to learn, then what we can say is, if we look at the area of the triangle given here, well, if we imagine that these were parallel lines going across here, then if I have a base and I have a distance between the two parallel lines, and we call that the perpendicular height. Well, that's really key in this situation, because if you just think about it here, if we had the base times this perpendicular height, then we'd end up with the area of a rectangle. So the area of the rectangle would just be base times height. But we know if we wanted the triangle, we had to halve the area of that rectangle. So remember what we did when we had the rectangle, we just had to halve it to get the area, and that's exactly what's shown on here. So as long as we've got the base, the height, that's not the slant height, on this diagram here, looks a little misleading. The h is this one here, which is the perpendicular height, the one at right angles. Then as long as we know the base times that perpendicular height, we just have to times them together, halve the answer, and we're always going to get the area of the triangle required. Even if we had a strange case like this, so if I keep this base the same, I'll change this colour to purple. So say if we had the base here, and we put the top part of the triangle somewhere around here, then what do we have? Well, B is the same, H is still the same, because it's still trapped between those parallel lines, so believe it or not, the area of that purple triangle is the same as the original white one. It's just base times height halved. Okay, so it's this perpendicular height that's really, really important. So let's have a look at the area of a trapezium now. Now, one way that I've taught this over the years, so if we just find a bit of space for ourselves here, is to just draw a trapezium like so. So this is a right trapezium, just one that has a nice right angle in it. Of course, the one on the formula sheet doesn't, but this will help you. If you call this length here A, these are right angles, okay, and this one B, and then just call this distance between them H, then if you were to do H times B, what would you get? Well, you would end up with a rectangle like so. And yes, that would be too much, wouldn't it? So that would be too high. If, and I'll change this colour, if I did H times A, then I'd get a rectangle which wasn't enough. So H times A would not be enough. So if you want to find the area of the trapezium that we started with, this one, then believe it or not, all we have to do is find the mean of these two answers. So we have HA plus HB halved. Now, for those that can factorise, if you take the h out as a common factor, you'll be left with a plus b all over 2. So what do we have in the formula given here? Well, we have a half. Well, I can see that there. There's our half in disguise, yeah? And we have our a plus b. There we have it. And then we have our h. So you can write this like this. H lots of a plus b all over 2, and that's exactly the same. So if it helps you to remember it that way, that's a good thing. Just think of it as being, and I'll use the actual one on the formula sheet here, turn it around and say to yourself, well, b times h would be an area too much, a times h would be something too small, so it would be h times a plus h times b all over 2. It would be the mean of those. And of course, if we factorise the h out, we're going to be left with exactly the same as we had before. So a very good visual is to think, that area's not enough, this one is too much, and so you kind of want the mean, okay? And you're always, every single time, you're going to get the area of the trapezium. It's all about the mean of rectangles. So what one can we look at next? I can just about see it. I think it would be this one, the area of a parallelogram. So let's have a look at that one. Well, a nice way of remembering this one is if you just imagine that you're just cutting this triangle off here, this right angle triangle, moving it to here. So we just cross this bit out and we're just left with, well, what are we left with? This height here, and what we've then got is this whole base here is preserved. It's this one here. So this is B now from here to here. This is H. So we've just got a nice rectangle. So the area of the parallelogram is just going to be base times the perpendicular height. That's really easy. In fact, it's so easy, I'm just going to check. Yeah, of course it is. There we have it. So it's just going to be base times perpendicular height. Always think perpendicular height, the one that goes straight up at 90 degrees from the base. Okay, so that's that one done. I think the next couple to look at would be the volume of a cuboid. Now, just think of a nice regular cube. So if I just draw one here, then if, say, for example, all of these were 1 centimetre by 1 centimetre by 1 centimetre, then the volume would just be all these dimensions multiplied by each other. And I'd be left with, well, 1 times 1 times 1 is just 1. And then I'd have centimetres by centimetres by centimetres, which would be centimetres all cubed. Okay, hence centimetres cubed. So in this case, just imagine, just visualise this cuboid as a cube. What would you do? Well, you'd end up with multiplying this length here, L, by this length here, which is the width, in this case, W, times this height here, which is H. Now a better way of doing that, and if I zoom into the actual picture, is I like to just choose a point on my cuboid and then try and say to myself, how was that point actually made? Well, in this case, it was made by this length, and this length meeting together to form that point. So all you have to do is just think about a point, how was it made, and you just multiply all of those lengths together. So in this case, this one here is L, this one here is W, and this one here is H. So what's the volume? It's just length times width times height. And you can use that nice memory technique here. So for this one, how was that point made? Well, it was a length by a width by a height. How's this one made? Well, it's a width by a length by a height. Doesn't matter which order they come in because you're multiplying them together. So that's quite a nice one. That leads me on to this cross-section by length business. What does that mean? It says, oh, we've got a prism here. So a prism, all that means is that you have a nice cross-section, you have some kind of strange area, but that area is repeated all the way along the solid. Okay, so this area is not going to suddenly fluctuate or change as it is pushed back to create the whole solid. So I remember, one thing I remember saying to a class is, imagine that you're in the snow, okay, so here's some snow here, and you just create a shape, say like a dustbin lid or something, and you put it on the ground, and you just jump on it, and it's going to push it downwards, and you're going to create a solid. In this case, it would be a cylinder. Now, if you wanted to work out the volume that you'd created, all you'd have to do is work out the shape that you started with, the area of it, and how far it was pushed downwards. And that creates a nice open space, which is the volume, and that's therefore the volume of the prism. Now, a prism is really special because if you have some kind of strange shape here, you'd have to push it down so that this shape was uniform or the same all the way along. So I'm going to find this hard to create, but I'll give it a try. So like so. It's not perfect, but what's here really has to be exactly the same as what's here. So my diagram's not amazingly good. That's probably a little bit better. So you can't have something that starts off here, pushes downward, and then somehow gets bigger. That's not called a prism, that's called a frustum. Being a prism is always about having a shape, pushing it down, and the same shape appears at the end. And if you join all these points up here, in this case you've got a triangular prism, basically like a Toblerone. So if you just think about it like this, join these points up, then this is the triangular prism. But it's this shape that's really important. It does not change. Okay, so sorry for going on about that one, but so many people get that wrong. So that brings me on to a cylinder, which is nice. So what we have to do here is, well, we have to find the area of this shape here, which is the area of a circle, and then we have to times it by how far it's pushed down, because we'll still end up with an area of a circle underneath. So I'm going to come back to that one. I'm just going to quickly look at the area of an actual circle, which is this one just here. So I'm going to create myself a bit of space here, and I'm going to do a little quick aid here to your memory, so you can think about how to find the area of a circle real quick. I'm going to draw 3 windows which are the same in terms of size. I've not drawn them brilliantly, but I'm sure you can grasp what I'm trying to get at once I've done them. So they're all identical. And I'm going to say to you that each of these lengths here is R, okay, in all directions. So all of these are R. So there's another one, okay, all of them are the same. So this is the same as this, is the same as this, this, and so on. So if I said to you, what's the area of all of this? Well, hopefully you'd say R times R is R squared, and I've got 4 of them. So it's going to be 4 lots of R squared. But what about if I said I want the area of this shape here? Well, hopefully you'd say, well, hold on, this is R squared and this is R squared, and I've got 4 of them, so wouldn't it be 4R squared? But think about it. Each one of these is cut in half. Look, all of them are cut in half. So you've really got 4R squared cut in half, which is 2 lots of R squared. And here's the thing that you can help, that will help you remember what a circle's area is. Some of you may know what's coming now. I'm going to change the colour here. So if I draw a circle here, then can you see that the area of this circle is definitely more than 2R squared, and it's definitely less than 4R squared. Now you might say it's 3R squared, and that's not bad. You can say 3R squared as a rough idea. But what is that number that's really close to 3 that you've heard of many, many times? Pi. Okay, so that's why the area of a circle is pi r squared. That's not a proof or anything, it's just some nice little diagrams that can help you remember it. So just think, oh, it's that number, it's 3r squared, but what's that 3? Oh yeah, that's pi, 3.141592.6, whatever you want to say. So you can put it on your calculator, learn it to 100 decimal places if you want, but that's the number pi. Okay, so the area of the circle is pi r squared. Let's move on to the circumference of a circle. Well, I like to remember it in this way, so I'm going to go and look at the diagram here, which I find really helpful. So here's my diameter. Now, did you know that if you took this diameter, say a piece of string, you could wrap it around the circle roughly 3 times. Now, so if you say d times 3 is all the way round, i.e. the circumference, well, if you see this strange 3 appearing, then you've got to think, well, it's not 3, it's that strange number again, it's pi. So you can say the circumference is roughly pi times the diameter. So if you just think c equals 3 times the diameter, that's not too far wrong, but just think it's not 3, it's this special number pi, which will be there waiting for you on your calculator, I can promise you that. Now, why does the formula sheet say something else? Well, it's no big surprise. The formula sheet says the circumference of the circle is, let's have a look, because it's probably in a slightly different way, it just says 2 pi r. Now, that's probably not the most helpful way of remembering it. What I try and say is, if I know from what I've just done that the circumference is roughly 3 times the diameter, i.e. pi times the diameter, I know, and this is where the diagram's really helpful, that 2 of these radii make a diameter. So I can just say c is pi times 2 lots of the radius. So you can just write it as pi times 2 times r, and multiplication can be done in any order, hence 2 times pi times r, or 2 pi r. Okay, so that's the circumference and the area done. Now, it does have this one actually, so it has pi times the diameter, and that's really good. So there's those 3 done. So let's just go outwards a little bit and see what ones we've done. Let's have a little recap and let's just see what's left. So I know what we've got to do next. We've done a lot of the rectangle, parallelogram, triangle, trapezium. We've looked at the cuboid, prism. Don't forget we were looking at the cylinder, weren't we? So the cylinder is now an easy one to know because you now know how to find the volume of a prism, and that's really what a cylinder is. So you know it's the area of one of the top faces, and we know that this is a circle of radius r, so the area is pi r squared, and yes, we're jumping down in the snow a height of h, so that's going to be the volume. Pi r squared times h, or just pi r squared h. Okay, if you want to write it as pi times r times pi times r squared times h, that's fine also. Okay, but if you want to miss the time signs out, just remember it's all multiplying, so it's pi r squared h, they mean exactly the same. Okay, so that's quite a few of these done. I think one reasonably easy one to remember is the compound measures. So if we look at, say, for example, the speed here, if you think of a speed in miles per hour, then when you say miles per hour, so let's just write it out in English, miles per hour, we know miles is a distance, we know hours is a time, and per means divide. Okay, so if we want a speed, which is what miles per hour is as a speed, say the speed of a car, then the speed is just the distance divided by the time. Okay, so when you're saying 80%, for example, so if you write that in English, 80%, well, what would that be? Well, in this case, you would write 80 divided by, because that's what per means, divided by, and cent means 100. So you'd have 80 out of 100, or 0.8. So if you think about speed is distance over time, then you can use your algebra to find the other ones. I'm not a great fan of formula triangles, I have to say, so if you want to talk about formula triangles, then you need to ask someone else. That's not me, and I know I'm probably going to get complaints from people saying, wow, they're really easy to remember. Yes, I'm sure they are, but it's not too much work to actually say to yourself, well, if speed is distance divided by time, then how would I find, say, for example, the distance? Well, what I'd have to do is I'd have to multiply both sides by t here, and I'd end up with speed times time is distance. But say, for example, I start from speed equals distance over time, and I wanted to find the time here. Well, what I could do is I could times both sides by t, and then I'd end up with s times t, I'll write that out again, s times t equals d, and then I think, well, I will need this time here on its own, so I'm going to divide both sides by s. And that would leave me with, well, t equals d divided by s. So time is distance divided by speed. Now, maybe I shall give in to you here, because I think for some of the foundation students, to be able to manipulate this formula here does show that you'd have to have some reasonably good algebra, which is needed for the foundation paper to get a 5, for example, a level 5. If you, for example, find that really hard, then formula triangles, so I'm going back on myself here because I don't plan these videos, I just go straight into them. So I will go back on what I said, so I apologise to some of you. To use the formula triangle, what you can do is, if you want to say, for example, find the distance, then you're kind of covering this one over and you're left with speed times time. If you cover this one over, time, it's going to be distance divided by, distance divided by speed. And if you want speed, think of miles per hour, the speed will be distance divided by time. That's what's left. Okay, so I'll go over that one more time. And if you get it, then just fast forward, you don't have to listen to this. Think of your miles per hour, and that's the speed. So think of your speed being miles, distance divided by hours, time. If you use the formula triangle, cover up the s, and what are you left with? Well, you're left with a distance here divided by a time, which is what you've got here. If you want the time, then you've got distance divided by speed, and if you want the distance, then you've got speed times time. Not a massive fan of that, but there you go. Now, for density as mass over volume, try not to say it like that. Try and say density is how much mass you can cram into a certain volume. So mass per volume. So if you think about it, if you had a cuboid like so, and that's a given volume, if you can cram more mass into that given space, it's going to make it more dense, i.e. you're going to have more mass per given volume. Okay, so if you think about it, if this number here on the bottom is constant, i.e. a given container, but we're able to squeeze more mass into that container, then this fraction, this number's going to be getting bigger, this one stays the same, it stays constant. So you're going to end up with, say for example, say we had the volume of this cuboid was 1 units cubed. But then I put, 1 kilogram of mass in it. Well, what's 1 divided by 1? It's 1. But if I could squeeze 11 kilograms of mass into the same volume, I would have 11 divided by 1, which is 11. So it's actually gone up. What's gone up? It's density. Okay? So the more mass you can cram into a given volume makes the density more. Okay? So think of density as mass per given volume. It will help you remember it. Another one here is, if you think about pressure, think of it as force applied per given area. So for example, if you had a situation where you had a square meter on here, and if you put as much force as you could onto this given area, then that would increase the pressure. But if you had less force applied to the same amount of area, then the pressure would be less. Okay, so think of the pressure as being the force per given area. Okay, and that will help you remember that one. And you can use formula triangles for these as well. I'm not quite sure how you'd remember the order of how to write these, but I'm sure you can work out a little way to remember, because it's only got 3 letters in each one. Okay, so I think you probably use these ones in physics as well, if I'm not wrong. Probably chemistry, maybe biology too. Okay, so that's those 3. And then I think that just leaves us with, and I'm just going to check through the ones that we've done. So I'm just going to check these quickly so I don't miss any out. So we've done this one, we've done that one, yep. These 3 are done. The Pythagoras we've not come to yet, and we haven't done these ones, so these ones definitely need doing. We did these ones at the very beginning, the higher ones, and we looked at the foundation ones afterwards. So we've done all of those. It just leaves us with Pythagoras and the trig ratios. So I think Pythagoras is quite tough. For higher students it's not quite so bad, but for foundation students it can be really difficult. I think if you had a right angled triangle, and I'll just use the one that it had in the formula sheet, it said A, B and C. Try and think of it like this. I know it's difficult, and especially if you've left this till the last week or so, try and imagine that there's squares on each of these sides, and they've all got to come out at right angles. Okay, so there you go. There's 3 squares here coming out. Then all you've got to think about is this. What's the longest side of that triangle? Well, the longest side of the triangle is always the one opposite the right angle in the triangle that you started with. So basically, this is going to have the biggest area. So we're going to call this C here, and that's going to be the biggest area. And how do I find that area? Well, it's just C multiplied by C, because don't forget, this is a square. So this is going to be C squared. We're going to call this area B, and what's that going to be? Well, it's going to be B times B, and that's just going to be B squared. And then this area here is just going to be A by A, so this is going to be A squared. And the thing about Pythagoras that's really nice is that the 2 smaller squares, the 2 smaller areas, always make the bigger one. So what's the area of the 2 smaller ones? Well, it's A squared plus B squared, and that's always going to make C squared. So if you had a problem, and this is where people get stuck, if you had, say, a length here was 10, and this one was 5, and we had to find this one here, some people make the mistake of thinking, oh, I know, it's 10 squared plus 5 squared is this one squared. Well, no, it isn't. Try and think to yourself, this is going to be the biggest area, so even if you just draw a square, just round it like this really quickly, and say 10 times 10 is 100, and then do 1 here really quickly in the exam, and that's 25, well, this is an unknown area, so surely this one, whatever that area is, plus this one makes 100. Well, question mark plus 25 is 100, means that question mark is, well, 75. So if the area of this one is 75, then how do you find this length? Well, yes, you square root it, because it's this length times this length that make the actual area. So once you've worked out, and this is really nice, the 2 smaller areas always make the bigger one. And as long as you know the bigger one is always opposite the right angle in the triangle, you can't go wrong. Okay, so that's Pythagoras here. Now, a way of remembering the last one here, which is the trig ratios, well, this is really difficult because I've got some videos on the unit circle and trigonometry. It's new to foundation. I don't know how it's going to go down very well with the foundation students. I think it's really tough. I'm not going to teach you how to get these. It's literally going to be the last 1 or 2 minutes that I'm going to be speaking about this formula sheet and the ones that you have to know. And that is, I'm just going to write this down, which I learnt when I was like, I don't know, 9 or 10 years old. I think it's SOHCAHTOA. And this is just a way of remembering how to remember these. So if you just say SOHCAHTOA, try and spell it as you say it. So SOHCAHTOA. And then you can say to yourself, the sine of the angle is going to be the opposite divided by the hypotenuse. So opposite divided by the hypotenuse. The cosine here is going to be the adjacent divided by the hypotenuse. And the tangent here is going to be the opposite divided by the adjacent. Okay, just as shown. But that might not help you too much if you don't know where the hypotenuse, adjacent and opposite is. Well, one way of remembering where they are in a given triangle in an exam is if you've got the actual angle here, it always looks to the opposite. Okay, so if you're using this angle x, you want to look, where's it looking? It's looking right opposite. And if you know that the longest side, the hypotenuse, is always opposite the right angle, then you know that ADJ, or adjacent, is the only one that's left. So that's one way of remembering SOHCAHTOA, or sine, cosine and tangent. And that's really coming towards the end of this video. It's gone on a little bit, only because I've just tried to do each one as best as I can to help you remember. You don't have to watch all of this video. You can just press the forward key and it will skip 5 seconds at a time, and you can just go into the one that you want to look at. I'll try and do a link at the bottom so you can just click into each formula, but I might not have the time because it's a really busy time of year, as you will all know. So just to recap, if you're sitting the foundation paper, you only have to know the ones that are in dark grey. Okay, and I've labelled those with F's here. And if you're a higher student, you have to know the ones in light grey, and it's expected you'll already know the ones that are given as foundation. One nice thing I think that's going to happen, in fact I'm almost sure, if there is a formula that's not mentioned here, it's more than likely going to be given on the exam paper next to the actual question. So say for example you had to use the volume of a cone, it would probably tell you that it's pi r squared h divided by 3, for example. So they would just say that next to the question. So don't stress out too much, try and pick out each of these in turn, find your own ways on how to remember them, and I wish you all the luck on getting these, because I can remember that far back and how it felt for me, and we had quite a lot to remember then. So good luck with that.